Stephen is the Field Operations Section Director at TxDOT Bridge Division, where he directs statewide support in the areas of bridge inspection, preservation, construction, and maintenance, and geotechnical engineering. And he is going to present on carbon fiber polymer use in Texas.
Jean pointed out the lowest ratings for poor bridges, so we're doing what appears to be the best, considering that condition ratings, or that the condition ratings that is basis for this good, fair, poor measure is all visual. So by the end of this presentation, you'll know what our secret is. Quick overview of the presentation. I'll be talking about bridge impacts, strengthening and recent research, fire repairs, ASR DEF repairs, corrosion protection, and then I'll just close with some closing remarks. Overheight bridge impacts is a serious issue in Texas. This is what you see here plotted are the number of known impacts that are reported to our office and Department of Motor Vehicles across the state. You'll see heavy number, large volume of impacts along the interstates, particularly there in West Texas, in Odessa, Midland area, and then in the more populated urban districts like Dallas and Houston. And that's because there's an older inventory of bridges with lower vertical clearances. We've seen an increasing cost of repairs as the number of instances of impacts increases. Number of known impacts that is reported here is probably on the order of 1/5, maybe 1/4 or 1/5 of the total number of scrapes and so forth. Of this 105, there's probably half or so that require repairs, but another 400 or so are typical scrapes. So when it comes to pre-stressed beams, CFRP, carbon fiber reinforced polymers, is primarily used for protection and repair. Back in, prior to 2013, we had this bridge protective assembly that was at a steel angle, and behind it was a piece of timber, a piece of wood that was intended to act to soften an impact blow. In many cases, though, the damage didn't seem to be affected by, there was not an apparent benefit of this steel angle. So we went to this bridge protective beam wrap. This is a carbon fiber reinforced polymer, again, wrapped around, wrapping the bottom flange of pre-stressed beams. And the intent here is to provide some protection, something that would act to dissipate the energy a little bit more. CFRP is more effective at containing minor impact damage, and again, we don't have the hazard of that piece of wood or a steel angle falling off. Everything's pretty well contained. Without CFRP, the impact damage is plainly visible. You can see it really clearly after the loose stuff is removed, and the damage extends for a significant length. When you do have CFRP, this impact just happened this past weekend, but when you do have CFRP, the CFRP acts like a bulletproof vest to dissipate the energy. The damage is contained relatively well, and the challenge, though, is that you can't see the full damage. You've got to probably remove a little bit of the delaminated CFRP, and then possibly your limits of repairs will extend a little further into the CFRP. It was noted earlier today that bidirectional wrap is preferred, and you can see that I don't think that bidirectional wrap was used there at the bottom, which you can see a side impact, kind of a tearing action, was contributed to the failure there. So had we used bidirectional wrap at the bottom flange, we probably would have seen a little bit better performance. Like I mentioned, CFRP contains and confines repair material. So after a bridge is impacted that didn't already have CFRP, our practice is generally to do the concrete repairs and then wrap it with CFRP, and this acts to contain the patch material. It prevents the possibility of unsound repair material dropping onto lower traffic, so it's kind of a belt and suspenders, if you will. We've used it to strengthen beams So if in cases where the impact was too severe that it resulted in damage to the stirrups, we've relied on CFRP shear capacity, and then we've also relied on CFRP to provide some longitudinal strengthening to the bottom flange as well, so to supplement the reinforcing or strands. And many times it serves as a sacrificial protection. We've got a number of bridges that have been impacted several times, and so we've got on-call contracts in some districts that it's a matter of, hey, we've got another beam impact, go on out, please fix the impacted beam, remove the CFRP that was there, determine the extent of damage, do the repairs, and come back over it with CFRP. Some bridges have been impacted as many as 6 times. There are concerns with CFRP used for impact damage girders. The installation is critical so that you do have that dissipation of energy. If you've got debonding of the application, then it's like a piece of paper that doesn't do well at dissipating the energy. There have been some premature failures due to poor bonding of CFRP to the substrate, but these haven't been significant. There's a concern that there's a potential for UV damage, so we apply a UV coat to all of our CFRP applications. And to date, we've had some CFRP in place for upwards of 20 years or so, and we haven't seen any indication of need to overcoat or to provide additional coating. Like I mentioned, with beams, it potentially conceals the issue, so it requires additional work to remove the CFRP. Finally, one additional issue of impacted beam repairs is that, and it's irrespective of if CFRP is used or not, but one problem that we've got is maintaining a history of strand loss and stirrup loss to where we're relying on CFRP used. In the case here, there were 4 strands that were severed. As it is, the couplers were staggered to accommodate fit. We elected to omit splicing of one of the severed strands. So as we're coming back to bridges that have been impacted previously, we're trying to make an effort to make sure that we splice all of the strands so that at least know that at one point we decided that we didn't need to splice all of them. Obviously, prestressed beams have a lot of additional capacity, especially for strength. Generally, prestressed beams are controlled by service level stresses. It's not a tremendous concern, but it's something that we're aware of that we need to make sure that we need to account for. Other impacts aside from beams, we've repaired bent caps and columns with CFRP. We've had a few research projects here recently on CFRP use. One had to do with strengthening of beams. This project focused on flexure and shear. Kind of the biggest takeaways that displacement can be an issue. Displacement capacity was approximately half of the displacement capacity of the unstrengthened beam. So if we're getting large deflections, we've got an issue. It kind of goes to the fact that we're making a less ductile system. So CFRP failure is more abrupt. The presence of flexural cracks influences the response of strengthened specimens. We've got a person in our office that swears by the use of anchors, says, hey, make sure that we use anchors whenever we can. I think after reviewing the report, I'm in agreement with him that CFRP anchors are critical. Debonding of the longitudinal CFRP material tends to start at the location of flexural cracks. That's the big basis for making sure that we've got our CFRP properly anchored. Long-term wetting and drying cycles hasn't had an influence on strengthened beams and sustained gravity loads, which is one area that had been a concern of ours for a little while. Doesn't seem to be a reason to be concerned. Sustained loading nor cyclic loading appears to be an issue. When it comes to shear, obviously a practical limit on the increase in strength that you're going to get from CFRP on shear capacity, and ACI and ASHTO have limits on that, just like they do on shear reinforcing for steel. When you're within a distance of A over D ratio less than 2, there's pretty much no benefit from CFRP strengthening. Again, in terms of shear, fatigue has been shown to be acceptable. And one more time, anchors are important Finally, bidirectional CFRP has performed better, and so that's kind of another recurring theme here, anchors of CFRP and bidirectional CFRP. More recently, we had, just this past year, we finished up a research project on the use of CFRP to strengthen inverted T-bends. It was a project that was suggested because we've got a lot of inverted T's, and so an inverted T is circled in red there. I think a lot of other states use them too. I think we're just gone overkill with them in Texas. The intent of this research project was to identify ways to strengthen caps that might be able to accommodate increased loads, so either for increased legal loads or increased lane configuration. So in the case of the picture on the right, there's a bridge there that currently carries 2 lanes. We're looking at restriping it to carry 3 lanes. So this research was intended to help come up with a feasible solution. 2 options were looked at. One was a complete infill between the beams and then wrapping that with CFRP. That's on the left there. And then on the right, on the far right, you see a typical section of just addressing the bottom ledge. So if we focus in on the full depth CFRP, the bottom right picture shows it more clearly, and what's shown there, I guess in the top, is an unmodified, unretrofitted inverted T testing condition. The bottom right is a retrofitted testing condition. We saw that while we only need about 15% increase in capacity, we were able to achieve somewhere between 120 and 180% increase in capacity for ledge, flexure, and punching shear. If we address just the bottom portion, just above the ledge, we're able to reach 120 to 155% increase in capacity. CFRP has also been used to address fire damage on concrete bridges. I'm providing this as an example to show the performance of CFRP Rack. This fire was in 2005. We did an emergency contract for repair of the fire. And then after the repairs were complete, we wrapped it in CFRP. The bridge was taken out of service in 2017, but this was the last routine inspection photo that shows that the bridge performed really well after 12 years of fiber wrap. CFRP has also been used to address ASR damage, to contain the pressure inside of the concrete member due to the expansion of the ASR. Confinement was introduced as a project in 2004, but 12-inch grid CFRP Rack was introduced. This was observed for several years and found to be effective, but we needed to introduce more containment. So in 2012, we installed 100% coverage to the columns. Today, the CFRP is holding up really well. The only cracking that's reported on the routine inspection is shown to be in the unwrapped locations, so the tie beams and the portions of the columns that are not wrapped. We've used CFRP to address chloride-induced corrosion. Once the repairs are done, to wrap it up in CFRP and act as a barrier to prevent infiltration. In 1970s and 1980s, a few bridges were constructed. In 1999, we had a research project that we had that was intended to wrap CFRP around chloride-contaminated concrete. We did do concrete repairs, but as late as 2019, the condition rating for many of these bridges is 8 for columns and caps. We did research on these bridges to confirm that not only do they look good, but underneath the CFRP wrap, there isn't active corrosion taking place, and we were able to confirm that half cell potential shows very low probability of active corrosion, and chloride samples also were taken that showed that there hadn't been a significant increase in chloride. Closing remarks or reminders, we like the use of these anchors. The research has shown that they're very effective. CFRP is very effective for preservation. We've had a lot of really good success with CFRP in Texas. TxDOT's experience with durability of protective coating has been very good. Minor issues with debonding, but no instances of deterioration through bathtub retention of water. This bathtub retention of water, you'll hear a lot of CFRP vendors making sure that you've got some way for moisture to escape. And to date, we've done a really good job of covering it up and sealing it up at the top so that chlorides and water doesn't infiltrate the outer surface. And we haven't seen an indication of a problem from this bathtub retention of water. Bidirectional layering improves the performance. I've already mentioned anchors, but I think it's important to at least consider the use of anchors. Significant strength increase on inverted T's can be achieved through CFRP. I think that's it. If there's any questions.
Just want to say in Florida, we've been using this for about 20 years at least. You know, we've done a lot of impact damage. It seems like you're doing a lot more than we do over here. We have by the way, we have a research project ongoing to try to figure out the durability of how long this stuff will last. And one of the things we're also concerned about is sunlight, but I don't know where that is right now. My question is this: for the fire damaged bridge, and you probably had some embrittlement due to the fire of the reinforcing steel. I guess you had to take that into consideration when you put in your CRP, right?
Yeah, I believe that was taken into consideration. There was a good amount of work that went into that assessment before deciding to go with CFRP. I might have a little bit of help answering that from Brian Merrill, who is likely involved in the project when he was at TxDOT.
Two kind of questions. One, do you guys use any of the carbon fiber bar reinforcement?
We do. We've got a standard for CFRP. Well, I guess it's glass fiber reinforced glass fiber. And that's the extent of our use for.
And who applies it? Is this state staff, or is this contract work, or who's actually applying it?
On these projects, contracted staff had been used to apply this.
Have you guys started doing this prescriptively, like done it in advance of bridges? Like you said, here's a bridge that's 14 feet, hasn't been hit yet. We're going to start, do it like on a quarter basis, kind of like a preservation action in advance, if you would. We
haven't started wrapping our beams as a preservation advanced action, except for the new standard where on new bridges we're applying CFRP wrap.
First one is, what's the cost of this FRP as you're putting it in there? And then the second one is, you mentioned that you looked at the half cell potential only. Is it corrosion that was the primary concern, or is it the structural, hit that was taken care of? That's the primary concern.
I'll go with cost first. CFRP wrap for at least beam repairs is about $10,000, $5,000 to $10,000 per instance. That's for kind of the moderate impact damage. I can probably get you a price on CFRP per square foot applied. Your second question, I'm sorry, that was half cell potential. For the chloride contaminated, and I don't think I'm going to answer this question, but for the chloride contaminated concrete, we took chloride samples on those bridges that were in Lubbock, and took half cell readings, and both those indicated that there was good performance from the CFRP. Looking back at what was done. No. That was corrosion. Corrosion was the issue, and so there wasn't strengthening on those bent caps, but we've done strengthening on other bent caps.
All right. Well, let's hear it for Stephen.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.